Hello everyone. In this video, I'm going to show you how you can streamline your calculation workflows in the Amsterdam modeling suite by setting up and running jobs in Python. As we will see, it is simple to convert your existing calculations to run in Python thanks to our scripting tools and integration with Jupyter Lab. And what's more, you can now submit these Python notebooks to run on your cluster with a few clicks in the GUI. As an example, I am going to show you how to calculate the intercalation potential for a range of materials based on lithium cobalt oxide, which can be used as cathodes in lithium-ion batteries. This property is important as it determines the cell voltage and therefore the energy density of the battery. To begin with, we can set up the first calculation for the energy of lithium cobalt oxide itself using the graphical user interface. So you can generate the structure using our crystal builder from the space group information. But it is also easy to load an existing structure from a CIF file, as I will do here. As you can see from the periodic view, we now have this layered structure with the lithium ions intercalated between the cobalt oxide sheets. So to calculate the energy, I'm going to run a geometry optimization with one of our machine learning potentials, N3GNet, with additional D3 dispersion. And this has been shown to give good accuracy compared to DFT whilst being more computationally tractable. Now ordinarily, you could just save and run this in the GUI, but here I'm going to select export as PLAMS script, which allows me to save this as a Python file. Next, I'm going to launch Jupyter Lab. For those of you who are not familiar with Jupyter Lab, it is an interactive development environment for creating and running Python notebooks, and is a great way to run calculations as well as analyze data. So here is the Python script that we downloaded from the GUI. And I could choose to run this with a simple Python command as shown here. But actually, what I have done is use this script as a template to build a full example notebook. And as you can see, this is quite nice, as you can add markdown comments, mathematical formulae, links to papers, and also split up your code in a very accessible and readable way. So we are now going to follow this short workflow to calculate the intercalation potential. And the key thing, which is what makes our scripting toolkit so powerful, is that we are going to do this not just for lithium cobalt oxide, but for a whole range of related compounds using a very simple loop. So here you can see I've created a list of transition metals and anions to loop over, and I've also created two basic functions. The first will simply swap out the cobalt atoms in the system for another transition metal, and the oxygens for another anion. The second function removes all the lithium cations from the structure. And then with these two functions, I can easily create the cross product of all these systems using a double loop. So for example, if I open the AMS GUI for the delithiated manganese sulfide structure, you can see that we have transmuted the atoms and we've flushed out the lithium ions from between the layers. Now using PLAMS, running these jobs in parallel is as simple as executing these two lines of code, which will take around a minute. So with N3GNet, you see that these calculations are very fast to run, even on a normal laptop. A further benefit of using Python is that we immediately have access to the full ecosystem of Python packages for data processing, analysis, and visualization. So here I use the pandas library to quickly collate all my results for all my systems in a single table. I then calculate the intercalation potential, and finally plot the results in an interactive graph, which allows us to immediately see the trends across this whole family of materials. Now one final feature I want to show you is that these Jupyter notebooks can be trivially submitted to run on a cluster using AMS jobs. simply select the notebook, choose your queue, and run in order to harness the parallelization of a compute cluster. Once finished, you can sync the completed notebook back to your local machine. So I hope this has helped demonstrate some of the benefits and the versatility that comes with running AMS calculations with Python. If you wish to find out more, please go to www.scm.com, where you will find further documentation, tutorials and support. Thank you for listening.